This this looks nasty. I haven't even read the problem, but okay. So let a, b, c, and d be the non-real roots of the equation x to the fifth equals 1. Then we want to evaluate this crazy expression. Well, one thing we can notice is that each of these fractions is basically the same. We're just plugging in a different root. So we can focus on one at a time and maybe they'll all equal something together, or maybe we could do the same simplifications to one as we do to all, and then hopefully that once we simplify them, it's in such a way that we can sort of get them all together, right? Now, I wanna, well, no. Okay, let's think about, I see a lot of a cubes, a squared, you know, and I'm just gonna refer to a as like a general root of this equation, right? But I don't know, it's like we don't have any information about a cubed and a squared, really. We know about a to the fifth, and this is a pretty short equation, right? And this tells us a lot through Vieta's relations. We know that these have to add up to -1 because, well, basically we know that 1, right? 1 is a root to this equation. And by the fundamental theorem of algebra, we know that this equation has 5 roots, right? 5 complex roots. And so, since we know that we have 4 non-real roots, the problem's kind of telling us that, but we can figure that a, b, and c, d are non-real. Um, but basically, since 1, right, 1 is a real root. So if we're just looking at what a, b, and c, and d are, right, if we don't care about what 1 is, then we should use polynomial division, right, to get rid of it. So we want to consider, instead of just x to the fifth, we want to know what is x to the fifth minus 1 divided by x minus 1. And some of you may not know this or not, uh, well, the way I think about it is that this form is the sum of a geometric progression with 5 terms. It starts at 1, and its common ratio is x. So putting all that together, we know that this is equal to the sum from 1 is just 1 plus x squared plus x cubed plus x to the fourth. And so now we get our sort of this expression, right? This expression is in each and every one of these things, right? And if we evaluated this at a, right? If we were to plug in a on both sides of this equation, we would get 0, right? That's the definition of a, and so on for b, c, and d, right? Because they're roots of this polynomial. But they're not just roots of this equation, right? They're also roots of this equation, because they aren't roots of this equation. Because obviously the only root of x minus 1 is just 1, and we know that a, b, c, and d are non-real. So we know that each of a, b, c, and d are the roots of this equation when it's set to 0. And so we see this a cubed plus a squared plus a plus, well, we don't have a 2 here, we have a 1, but that's fine, right? So we can say that each of our fractions is instead, let's say I take out the 1, right? So now we're just looking at what is a cubed plus a squared plus a plus 1. Well, if I subtract on both sides x to the fourth, we get that is equal to negative x to the fourth. I'll write negative a to the fourth. So we now have a new simpler expression for each of our fractions, right? But there's more, right? We know that a4, like, we don't really want to deal with fourth powers of roots, right? Because if we're gonna end up applying something smart like Vieta's, right? We want like linear or at most quadratic, like the sum of the squares of the roots, right? Because we can handle that. But this is a little unwieldy, a to the fourth. But what's nice about a to the fourth? Well, we know that since a to the fifth is 1, then we know that a to the fourth is 1 over a. So in fact, this fraction is just 1 over 1 minus 1 over a. And that's a huge simplification, right? So now we're just adding up fractions of this form for a, b, c, and d. But now let's think about, well, I can argue this in two different ways, right? Let's think about what a, b, c, and d are. Let's think about a geometric interpretation, in fact. We know that geometrically, if x to the fifth is equal to 1, then we know that we have some sort of special pentagon going on over here, right? Because these are roots of unity, and so they will form a regular polygon inscribed in the unit circle. And that might be a little advanced or scary for you. But the point is that if you have a sort of something on the unit circle, then you know that 1 over whatever, right? And we're not looking at this, so this corresponds to 1, right? And these are a, b, c, and d in some order. Um, then we know if we take 1 over something, and it's on the complex plane, that's the same as negating its angle, or taking the conjugate. So let's say I just order these. Let's say this is A, this is B, this is C, and this is D. Then it's pretty easy to see if we used uh, Euler's formula, right, to get complex forms for A, B, C, and D. We could see that A and D are conjugates, but more than that, we know that 1 over A equals 1 over, or 1 over A equals D, and 1 over D equals A. And 1 over B equals C, and 1 over C equals B. And so these 1 over A's, since we have a 1 over whatever in each fraction, then we know what can we conclude from that? We can conclude that this would be the same as taking the sum of all the fractions of the form 1 over 1 minus a. Because we can replace 1 over a with d, and we could replace 1 over d with a, and we could replace 1 over b with c, and 1 over c with b. So we're now taking this even simpler sum, right? Now we just have linear terms. And if you're not quite convinced, because I didn't really show all the sort of the trigonometric steps to proving that these are conjugate, another way of showing that uh, A, B, C, and D is the same set as 1 over A, 1 over B, 1 over C, and 1 over D, that's sort of what I'm claiming, right? They're the same set. Then notice this is a polynomial with roots A, B, C, and D. Try and find a polynomial with roots 1 over A, 1 over B, 1 over C, and 1 over D. How can you do that? Just by plugging in 1 over x for x. That will give you the reciprocal. But after simplification, you get the same polynomial, which means that the roots 1 over the numbers 1 over A, 1 over B, 1 over C, and 1 over D are the same as the numbers A, B, C, and D, and some order, right? But order doesn't matter because we have a cyclic sum, right? This is a cyclic sum, which I talked about some in base-centric coordinates. So really I should have the word, or the letter CYC here. This is cyclic. So now we need to figure out a way to get this, right? One method of attack would be find a polynomial with roots 1 minus a, and then you can figure out the polynomial with roots 1 over 1 minus a, and then use Vieta's to find that sum. But the method I most prefer, right, and this involves a little bit of calculus, so if you're just a sort of a high schooler, and you know, because this is an AIM type problem, right? This could appear on the AIME, and so you would want sort of an algebraic way to do this, and I'm providing all the proper hints of how to do that, right? Just polynomial manipulations is how you're supposed to solve this problem. But I'm going to share a method that is really cool, right? So imagine we combined all these fractions now, right? The denominator is going to be 1 minus a times 1 minus b times 1 minus c times 1 minus d, right? So I'll draw that out. Right, so we found a common denominator, 1 over a, or 1 minus a, and so on and so on. But this form, right, we know that a, b, c, and d are the roots of this polynomial, right? And so what I can do is make space here, so hold on. Alright, so I'm going to let f of x equal this polynomial, right? And so we can write it in factored form because we know a, b, c, and d are the roots, or, that's what we're defining them as. So now it becomes very clear that this expression here is just f of 1. So we know our denominator. But what's our numerator going to be? Well, for each fraction, right, we had just one of these terms, 1 minus a. So the numerator for each fraction has to become the product of 3 of them. So 1 minus b times 1 minus c times 1 minus d plus, and so on, right? So we have 4 of those expressions. And let's think about taking the derivative of this polynomial, right? This polynomial with 4 distinct roots. So it has 4 distinct linear factors. Then if we take the derivative, then by the product rule, the product rule, we take the derivative of the first times this junk, and then the derivative of this times this junk, and basically so on and so forth. So, but the derivative of whatever factor is just 1, right? Because they're all linear monic factors, so they have a coefficient of 1 for the x. So we're just going to get those 4 sums of 3 terms, right? So this numerator is actually going to be f prime of 1. So what that tells us is we can just take the derivative here. So we get an expression for the derivative of f of x. And by that product rule argument, we know that each of these terms will be, the product of 3 of the linear terms at a time. And then for x, we just plug in 1. So we're plugging in f prime of 1 instead. So now we can finally say what this expression is. It's f prime of 1 over f of 1. And f of 1 is just 1 plus 1 plus 1 plus 1 plus 1. That's 5. That's easy. And then this expression is 4 plus 3 plus 2 plus 1, which is 10. So, lo and behold, the final answer is just 2. Wow, this beastly expression just evaluated to 2. Man. See, algebra problems like this that appear, usually late Amy, and this wasn't actually on an Amy. This is inspired by another problem I've seen before. I just changed some numbers. But problems like this, right? They that have like nasty expressions, right? You just have to use what is given to you in a clever way, right? Instead of having all these sums, right, we just get rid of them by replacing them with a to the fourth. And then we know that a to the fifth is 1, so we can just replace a to the fourth with 1 over a, and then 1 over a with a, right? It's just a chain of sort of realizing what it has been given to you. So anyway, thank you for watching. I hope you enjoyed this problem as much as I did. I love this problem. But anyway, I will see you in my other videos.